Somewhere above you at this very moment, a piece of metal is sitting in direct, unfiltered solar radiation. No clouds overhead, no shade to break the light, no atmosphere in the usual sense to soften the energy hitting it. And yet, that metal is not heating up in the way you would expect. It remains stable. In fact, it can stay cooler than the surrounding environment itself. There is no electrical input, no ventilation system, no rotating machinery, nothing moving at all. It simply exists under one of the harshest light environments available, and it quietly resists temperature rise. That object is a spacecraft, and the technology keeping it stable comes from the same institution that once landed humans on the moon. But there is something most people are never told. The physical principle that keeps high-value satellites from overheating while exposed to full sunlight is not hidden behind classified systems. It is established physics. It has been tested on Earth, including rooftop experiments, and a low-cost version of it can be prepared using basic materials for roughly $40. For many years, industries that profit from conventional cooling systems had little incentive to highlight this method. There is no advantage in promoting a passive approach when active machines generate ongoing energy consumption and recurring bills. As a result, the knowledge remained mostly within technical papers and academic documentation, visible but not widely discussed. Now that changes. The goal here is to understand how a surface can remain cool under direct sunlight, the scientific basis behind it, and how a simplified version can be constructed in practical conditions. To understand NASA's approach, the real situation in space must be considered first. In the vacuum outside Earth, there is no air. Without air, there is no convection. A spacecraft cannot rely on airflow like a car radiator does. There is no wind, no circulation, nothing to carry heat away. So heat management in space depends on a different mechanism entirely. A spacecraft releases thermal energy by emitting it outward as electromagnetic radiation, essentially sending heat away as invisible light into space. Because of this, engineers developed specialized white thermal coatings. These are not ordinary paints. They are engineered surfaces designed with two key behaviors. First, they reflect most incoming solar energy, meaning very little heat is absorbed in the first place. Second, they are highly effective at emitting infrared radiation, allowing internal heat to escape efficiently. NASA technical documentation describes this clearly. These coatings combine low solar absorption with high infrared emission. In simple terms, they take in minimal sunlight while releasing heat effectively. That balance is the core mechanism. A surface that absorbs very little energy while efficiently radiating heat will remain relatively cool even under direct solar exposure. So when it is said that a structure can stay cool in full sunlight, it is not speculative. It reflects the same thermal control principle used on operational satellites orbiting Earth. The remaining question is whether this same effect can function within Earth's atmosphere. The answer, demonstrated through rooftop testing, is yes. Every object that has heat emits energy in the form of infrared radiation. Human bodies do it, roads do it, walls and rooftops do it as well. Most of this infrared energy is trapped near Earth's surface, bouncing between air, ground, and clouds. That trapped energy is one reason urban environments retain heat even after the sun sets. However, there is a specific exception. Scientists refer to it as an atmospheric window. Within a narrow infrared range, roughly between 8 and 13 micrometers, the atmosphere does not significantly absorb radiation. Light within that precise band moves straight through the full thickness of the atmosphere and continues outward into space. There, it reaches a background temperature close to the near absolute cold of the universe, far below anything experienced on Earth. It behaves like a thermal exhaust channel. Most surface heat remains trapped close to the ground, circulating within the lower atmosphere. But when a surface is engineered to emit energy in that specific infrared range, it effectively gains a direct pathway for heat to leave the planet. The heat is no longer confined to lateral movement into surrounding air or nearby objects. It escapes outward into space itself. When this outward radiation pathway is combined with a surface that strongly reflects incoming sunlight, a balance is created. Minimal solar energy is absorbed, while internal heat is continuously released through that atmospheric window. With a correct ratio, the surface does not merely stabilize near ambient temperature. It can fall below it. In such conditions, the surface becomes colder than the surrounding air even while exposed to direct sunlight. This outcome appears counterintuitive until the role of the space-facing infrared pathway is understood. This is not theoretical. It has been tested in real-world conditions on a rooftop under full daytime sunlight. A research group at Stanford University constructed a specially engineered layered material and exposed it outdoors during peak solar intensity. The surface reflected approximately 97% of incoming solar radiation while simultaneously emitting thermal energy efficiently through the atmospheric infrared window. Their published findings were significant. Under direct sunlight during the brightest period of the day, the material reached a temperature approximately 9 degrees Fahrenheit, or 5 degrees Celsius, lower than the surrounding air. The sunlight was still directly striking the surface, yet it remained significantly colder than the ambient atmosphere. No electrical input was required. No refrigerants were used. No mechanical systems were involved. Only material design and radiative physics were responsible. These results were peer-reviewed and published in the journal Nature, confirming the validity of the experimental outcome. This marked a shift in understanding. Radiative cooling was no longer limited to nighttime conditions. It became a daytime cooling mechanism under full solar exposure. Earlier assumptions held that sunlight would always overwhelm this effect, but the Stanford experiment demonstrated otherwise. With the correct surface properties, radiative loss to space can exceed solar gain even at noon. The radiative channel to space remains open continuously. However, the material used in that Stanford experiment relied on complex multi-layer engineering that is difficult to reproduce without specialized fabrication. The next development focuses on simplifying this approach for practical use. It centers on a widely available white powder. That material is barium sulfate. It is a simple white compound used in applications such as photographic paper production and cosmetic formulations. It is neither rare nor expensive. Researchers at Purdue University found that when this powder is incorporated into paint at very high concentration and engineered with a wide distribution of particle sizes, the resulting coating achieves extremely high reflectivity. It has been measured at about 98% reflectance of sunlight. This performance was so high that it was recognized with a Guinness World Record as the whitest paint recorded. But the significance is not the record itself. The key factor is its cooling behavior. In controlled sunlight testing, surfaces coated with this material reach temperatures about 8 degrees Fahrenheit, or 5 degrees Celsius, below ambient air conditions. At night, without solar input, the same surfaces drop by as much as 19 degrees Fahrenheit, or 5 degrees Celsius, below surrounding air. Conventional commercial white paints typically reflect between 80% and 90% of sunlight. They generally do not produce temperatures below ambient air at all. This represents a fundamentally different performance range, built on the same radiative physics principles used in spacecraft thermal control systems in orbit. The final key element is particle sizing. Researchers found that when particles vary across multiple sizes, each size interacts with different portions of sunlight. Together, they scatter across a much wider portion of the spectrum, reflecting nearly all incoming solar energy as a combined effect. There's another important condition stated clearly in the research. If the goal is to push the surface below ambient air temperature, the coating cannot be thin. Measurements showed the layer needs to reach roughly 400 micrometers in thickness. In practical terms, that means multiple full coats rather than a single light application. With these three principles established, high concentration, mixed particle sizes, and sufficient thickness, the construction process can be defined. The method is straightforward in structure, but requires precision in execution. The performance depends not only on materials, but also on placement and preparation. The first step is selecting the base surface. It can be applied to an existing exterior wall, but for initial testing, a detachable panel is more practical. Materials such as cement backerboard or exterior plywood are suitable choices. The surface must be fully cleaned before anything is applied. Any contamination, such as dust, oil, or remaining old paint, will weaken adhesion and reduce effectiveness. If the surface is raw, it should be sealed first with a basic exterior primer and allowed to fully cure. A stable and clean foundation is essential. The second step is gathering materials. The base coating should be a high-quality white exterior paint. One of the more accessible options is an elastoic white roof coating commonly used for cooling flat rooftops. This alone already provides strong reflectivity. The key additive is barium sulfate powder, sometimes sold under names such as Blancix or as a Barrett-based pigment available through ceramic, pottery, or pigment suppliers. A simple infrared thermometer is useful for measurement, along with a roller, brush, mixing stick, and a bucket. The total cost typically remains close to $40 depending on what is already available. The third step is mixing the coating. The white base is poured into a container first, then barium sulfate powder is gradually added while stirring continuously. The objective is to incorporate as much powder as the mixture can hold, while still allowing it to be applied smoothly. The stirring must be slow and consistent to avoid trapping air. Additional powder is added until the mixture becomes dense, highly opaque, and strongly white, but still usable with a roller. The principle is simple. Increasing the concentration of scattering material increases the amount of reflected sunlight. Dilution reduces performance and should be avoided. The fourth step is application in layers. This stage determines success or failure. A single coat is not sufficient. The first layer is applied evenly and allowed to dry completely. Then a second layer is added, followed by a third. The goal is to build a solid, thick, white coating that reaches the required depth. The research shows that below a certain thickness, cooling below air temperature does not occur. Thin coatings reflect light but allow heat retention. Thick coatings maintain reflection and enable cooling performance. Each layer must fully dry before the next is added. The final finish should be completely opaque, with no translucent areas. The fifth step is orientation toward the sky. This factor determines whether the system performs at its highest level. The radiative pathway to space depends on direct exposure to open sky. A flat or upward-facing surface radiates heat far more effectively than one blocked by structures or shaded by overhangs. The top portion of a wall performs better than lower sections. A tilted panel facing upward improves performance further. Nearby heat sources, such as concrete or metal surfaces, should be avoided, as they can reflect thermal energy back into the system. The surface must maintain a clear line of sight to the sky to fully utilize the atmospheric window effect. When all these conditions are combined, the result is a passive cooling system driven entirely by material physics rather than mechanical power. This completes the process. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.